Alright, so today I'm going to be explaining this interesting paper with the title Blaring Diffusion Models. Because most diffusion models, specifically especially in images for computer vision, they see it as a Gaussian noise. But this idea of blaring is interesting because you can use this convolution to make a blurred version of the sample. So this paper in ICLR 2023 by Google Research. So in 2022, they have presented a new type of diffusion process for generative modeling based on heat dissipation or blaring as an alternative to isotropic Gaussian diffusion. Here we show that blaring can equivalently be defined through a Gaussian diffusion process with non-isotropic noise. So it's the same idea, but we can have a non-isotropic noise. In making this connection, we bridge the gap between inverse heat dissipation and denoising diffusion. So they shed light on the inductive bias that results from this modeling choice. So they propose a generalized class of diffusion models that offer the best of both standard Gaussian denoising as well as inverse heat dissipation. So they call it blaring diffusion models. You typically add isotropic noise, but you can think of heat diffusion as a low-pass filtering. So we call it blaring kernel, or B. So what is B? In next slides I have shown here, B is just this convolution. It's an operator. And this is the Gaussian kernel that you're using it. This is how they beautifully showed. So you see the comparison between standard diffusion, the heat dissipation diffusion. So instead of noise, which is here we do it blaring. Even with blaring, we can capture. Heat dissipation, but this is a combination of those. For blaring, it's a combination of diffusion and blaring and heat dissipation. So we model the diffusion process as this normal distribution, and Z is the noisy latent variable. X is your data. So because it's a Markov process, we have this. This is a normal distribution. The transition can be defined like this. So when we do denoising, to generate data, the true denoising process is approximated by just learning that denoising process. This is our denoising process. So we are learning it, and instead of directly predicting X, some diffusion models work on the noise. Some of them mean, some of them noise, some of them original. But this paper is like DDPM, if you remember. So this is how they just model the log likelihood by just this expectation over squared reconstruction errors. So you need to have a background on inverse heat dissipation. This paper, Risanen in 2022, they observed that Laplace partial differential equation for heat dissipation can be solved by a diagonal matrix in the frequency domain of cosine transform if the signal is discretized to a grid. So if Z is just the solution of the Laplace equation, so this can be efficiently solved. The BV transpose here is just the discrete cosine transform, and V is just the inverse discrete cosine transform. So for a specific definition of lambda, a weighting matrix for frequencies, you can see that reference this in 2022. So the intermediate diffusion state is thus constructed by adding a fixed amount of noise to an increasing blared data rather than adding an increasing amount of noise as in DDPM that I've explained it in a different video. I mean, this one is like a very, very highly cited paper that many ideas come from that. But we can also generalize that, as they have done by combining with that idea of heat dissipation, you will see. So what is arbitrary dissipation schedule? There is no reason why the conceptual time steps of the model should match perfectly with the dissipation time. Therefore, if you write dissipation to be e to the minus lambda tau, it's a monotonically increasing with t, and tau has a very similar function as alpha and sigma in noise diffusion. So the open question is, can the heat dissipation process be Markov, and if so, what is the transition kernel? Is a true inverse heat process also isotropic as the generative process in equation 11? And finally, there are other alternatives to predicting the mean of the previous time step. So the first question, can the heat dissipation be Markov? Yes, the process can be Markov. As a result, the denoising equations similar to the ones for standard diffusion can be derived. Is a true inverse heating process isotropic? No, the inverse is not. Generative process is not isotropic, although it is diagonal in the frequency domain. So we can think about heat dissipation as a Gaussian diffusion. So we interpret it as a Gaussian diffusion. So we see this marginal distribution, and A here is just the blaring or dissipation operation as defined in the previous section. So we let V transpose denote the orthogonal discrete cosine transform, which is a specific normalization. If you just use a change of variable, then you will see that this U here, instead of X, you have U, it's just change of variable. This U is the frequency response of X. So now this equation shows that the marginal distribution of the frequencies is fully factorized over its scalar element. Similarly, the inverse heat dissipation model is also fully factorized. So we can equivalently describe the heat dissipation process in scalar form for each I. And this is just the special case of standard Gaussian diffusion process. This was the motivation for this paper. So an open question is whether or not there exists a Markov process that corresponds to their chosen marginal distribution. Though its equivalence to Gaussian diffusion shown above, we can now answer that question affirmatively. Yes. So we have that this process is given by this, and if we substitute for alpha and sigma, you can derive the alpha and sigma in terms of D. And if D is chosen so that it contains lower values for higher frequencies, then sigma will add more noise on the higher frequencies. So you see a blurred, that change of variable, you see it here. This change of variable. From Z, we go to U. So a blurring diffusion process is diagonal in frequency domain under the change of variable. This results in a corresponding diffusion process in frequency space. So here we go to frequency space. So now that we are in frequency space U, all transition, you do everything that you know in the U space, in the frequency space. And luckily, we can find an analytic expression for the inverse heat dissipation process. So different from traditional models, the diffusion process is in frequency domain, U. And for learning, we know reparameterization. We are very good at reparameterization. So why not reparameterize it with alpha and sigma? I mean, U can be defined as this. This is the change of variable. And also similarly for U epsilon. So we can generate samples very easily like this. After blurring the diffusion and for optimization, we use this. We optimize unweighted square error. So in pixel space, we have this in pixel space Z, and you see it in equivalent space U. So to specify the blurring process precisely, the schedules for alpha and sigma need to be defined. For sigma, we choose the same value for all frequencies. So these are the technical things for implementations, just some hyperparameters, tuning. And also a limitation of blurring is that the use of blur has a regularizing effect. When using blur, it takes longer to train a generative model to convergence. Such a regularizing effect is often beneficial, can lead to improved sample quality.